Okay, so let's start with dedicated designs. I will start with MD4. It was developed by Ronald Rivest in 1990. It has a block size of 512 bits. Message digest length is 128 bits. Number of runs are 48. It is a Merkle-Damgard construction. And A, B, C, D are state words of 32 bits. MI is the ith message word. So since the message digest length is 128 bits, this is actually of that size. This is why all of these AIs are 32 bits. So in total, you have 128 bits. Initially, you fill it with IB. And once you start running this algorithm, you keep feeding your message words from here. Although your message block has 512 bits, here you feed them 32 bits by 32 bits, okay? So it is a very simple round function. So there is an F function here, which consists of ANDs or NOT operations. I will show them what it is in the MD5 because it is the same there. So you combine three words here, and the result is added to A here, and this addition is modular addition. So it is a 32-bit addition. You feed the message of 32-bit of your message here. You also add a constant here, then perform a rotation. Then, this word becomes B here, and B becomes C, C becomes D, D becomes A. Then this is your single round. You take this value, put it here, and perform the second round. So it has 48 rounds, okay? The thing is that the generating a collision takes a few microseconds on a laptop. So finding a collision for this hash function is really easy. The best publicly known result says that you can find the preimage by performing 2 to the 95 operations. But since this is an old algorithm, people didn't work much on them. Maybe if you focus on it, you can find better attacks, or maybe intelligence agencies already discovered better attacks, okay? So it was IATF standard hash function defined in RFC 1320, and it was retired in 2011. Just see that such a bad hash function was used until 2011, okay? It influenced later designs like MD5 or SHA1 or Ripemd. So if you look at MD5, the unfortunate thing is that people still think that this is secure. I teach to Turkish high school teachers that teach computer science, let's say, and they thought that they were teaching MD5 in their lectures as if it is a secure algorithm, and they kept using it for their personal use. Unfortunately, it is not. So it is again developed by Ronald Rivest in 1995, to replace MD4. The block size is the same. Message digest length is the same. But as you can see, number of runs are increased now. Instead of 48, you have 64 runs to make the attacks more complicated. But again, there's another change. You have an extra addition here to make attacks more harder. So I told you that I haven't mentioned what F is. So it takes three inputs, three 32-bit values, B, C, and D. And for the first 16 runs, what happens is as follows: B and C, or not B and D. In the following 16 runs, this F function acts like this: B and D, or C and not D, and so on. As you can see, it is just logical operations like AND or XOR or operation. So it is a very simple operation here. And again, finding a collision is really easy. Generating a collision requires 2 to the 18 operations. This is less than a second in a laptop. There are preimage attacks, which requires 2 to the 123 operations. As you can see, this is faster than brute force attacks. So in 2004, it was shown how to create a pair of files that share the same MD5 checksum. In 2005, Lanstra, Wang, and Weger demonstrated construction of two X.509 certificates with different public keys and the same MD5 hash value. In 2008, it's shown how to fake SSL certificate validity. So certificate authorities should stop using MD5. And in 2012, authors of Flame malware used MD5 Collision to forge a Windows code signing certificate. As you can see, something badly broken years ago, and we still suffer from it in 2012. Okay, so this is why when a cryptographic function is broken, you should stop using it. This is why when I say SHA1 is broken, I really mean it. Finding a collision means that a few years later, we will be able to have a malware like Flame malware that uses SHA1. Okay, this is why you should stop using SHA1. Okay, here's an MD5 collision example. This X1 is a one block input, 512 bits, and this X2 is different, and the differences are shown as red. So here, for instance, you have 7, here you have F. In the hexadecimal notation, 7 means that 0, 1, 1, 1. Here it is 1, 1, 1, 1. So the first bit is flipped. So this is what actually differential cryptanalysis works. So you make small changes by flipping a few bits, as you can see here. In here you replace A with 2 and so on. But use simplest flipped like 6 bits, but you obtain the same hash output. So this is an example for a collision. Okay. So if you're still using MD5 for some reason, you should stop it. And in my opinion, you should also stop SHA1, which I'm going to explain now. So SHA1 was developed by NSA. Actually, it was first published in 1993. But then 2 years later, they added a single bitwise rotation. I think it was this one, I'm not sure. So the initial version is referred to as SHA0. This modified version is referred to as SHA1. And as you can see, it is still, again, the block size is the same, but the message digest length is now increased by 32 bits. Because now we require 80-bit security when SHA1 was introduced. This is why we had to increase the output size. For this reason, now we have another word E here. Okay. So the idea is very similar. There's a F function here. You have the message words here. The constant is here, and operations are performed. But now the number of runs are 80, increased again. So it will be much harder to find collisions. Here's an SHA1 example. I think I used the one from NIST documents. I'm not sure, but this is what happens when you actually take the hash of a text. Okay, so our input message in this case written not in hexadecimal but as a text value. Okay, these are characters ABC. So in your keyboard, create a text file, put ABC inside, then calculate the hash of it using SHA1. The output will be the one as I shown in this slides. So initial hash value is actually the IV here. Okay, so the block contents that you are going to feed from here as WIs are written in here. As you can see, we said that the block size is 512 bits, but you have only 3 characters, right? In the hexadecimal notation, ABC will be represented by 61, 62, and 63, right? So these are the characters you put. Now we have to perform a padding. I told you that the padding works as follows. You put a single bit of 1, then you fill the rest of the block with zeros. This is why you have 80 here, okay? And zeros goes in this way. So at the end of the block, you actually write here the size of the input message. So as you can see, this is 3 characters, which means 3 bytes, which means 24 bits, right? So if you want to write 24, you have to write it like this in the hexadecimal notation. Okay. So as the round outputs, it is written like this. If you perform the operations, after 80 operations, this is your output. You write it here. You also add it to the initial values written here, H0s, H0 to H4. This addition is not an XOR, but real modular addition 2 to the 32. and the result is here. So this is the hash of the ABC text. Okay, this is how a hash function works. So keep that in mind when in the background when you perform a hash function. Actually, this is what happens. But of course, we don't want to use the SHA1 anymore because there is an attack that requires 2 to the 63 operations. So for the generic attack collision resistance, you know that 2 to the 80, right? Because the output has 160 bits. We said that the birthday paradox reduces the security to half. So a brute force attack requires 2 to the 80 operations. But years ago, Wang actually found a collision attack, but in theory, not in practice. So years ago, we knew that there was an attack to this hash function, but nobody found a real collision. But this actually affects the decision of Satoshi when he designed the Bitcoin. So this is why he included Ripemd, okay, to replace SHA1. Interestingly, SHA0 can be broken in a very fast way. This is why NSA actually realized this and updated it. But still, due to this theoretic attack, browsers of Microsoft, Google, and Mozilla stopped accepting SHA1 SSL certificates by 2017. Maybe you remember that time at the 1st of January in 2018. You tried to visit some web pages, but your browser made a red warning saying that it is not secure. This was because of this change, okay? They stopped accepting SHA1 certificates. Again, Bitcoin script allows SHA1 with opcode op SHA1, but it is not used in practice and you shouldn't use it if you write your own transactions. So in 2015, first collision example is obtained, but this is a free start collision, meaning that the IVs are different, as you can see here. Actually, not the different, but different than the specified version, let's say. This is different than the NIST documentation. Okay, so this is the M1, this is M2, and as you can see here, IV2 has a 0 here, it has 20 here. So it also introduces the difference to the IV. Again, this is why we call it a free start. Normally, once you fix an IV for a hash function, you use it for the rest of your life, right? Here, the attacker uses 2 different IVs and call it a free start, and both of them provide the same output. So this was found by using 64 GPUs, which actually they performed 2 to the 57 SHA1 evaluations to obtain this. A free start collision breaks the inner layer of SHA1, does not directly translate into a collision of the full SHA1 because the attacker is not able to choose the initial internal state. So actually here Mark Stevens was trying to prove is as follows. He's saying that with 64 GPUs, I can do this. So if I had more GPUs, I could really find you a real collision. This is what he was trying to show. And actually, once he published this paper with his co-authors, Google contacted them and said that we had a farm of GPUs. We can't tell you how many we have. We can't allow you to go and use them. Just write your code and we will run it on our servers and we will give you the result. So they did this years later and they obtained a real SHA1 collision like this. And interestingly, this collision is not on 1 block, but on 2 blocks. As you can see here, the IVs are the same. So this is why it is not a free start collision, but it is a real collision. So these 2 message blocks are different. Differences are shown with color, but the obtained hash values are the same. Okay, so this means that you can actually, if you put these inside the file, you will have 2 files with the same hash value, which would actually break any cloud service if they use SHA1. Okay, this is why you should stop using it. Let's move on to Ripemd. It looks almost the same. The places of the rotations are somewhat different. Again, it has 80 rounds, but the good thing is that there isn't any collision attack faster than the birthday paradox. Okay, This is why Ripemd 160 is the only remaining 160-bit digest size hash function that has not been broken yet. It was developed in the open academic community in contrast to the NSA designed SHA1 and SHA2. So this is why Bitcoin script allows Ripemd with the opcode op Ripemd 160. Moreover, Bitcoin uses Ripemd after using SHA256 for address generation with the opcode op hash 160. This is how most of the Bitcoin addresses are generated. Okay. So let's move on to SHA2. It is again developed by NSA and published in 2001. This time the message digest lengths are increased and it allows 4 different message digests. But in practice, we almost always use 256 or 512, depending on the use case. And for some bizarre reason, some TLS communication is done using this. And I believe this is because there was a bug in some of the operating systems 512-bit implementation. This is why they use this. Okay. It is again Merkle-Damgard, but again, now you can see that there are more functions involved to make things more complicated. And these functions like majority or sigmas are defined like this. This time the sigmas are adding a value to itself by rotating itself. Right. So now you put a to this function and it adds the rotation of a to itself. So it is a little bit more complicated. And currently the best pseudo collision attacks breaks 46 rounds. So there isn't a full attack yet. And again, preimage resistance is good. At 2011 attack breaks preimage resistance for 57 out of 80 rounds of SHA-512 and 52 out of 64 rounds for SHA-256. So this is why we trust SHA-2. Nobody could break it so far. Bitcoin script allows SHA-256 with opcode op SHA-256. And Bitcoin opcode op hash 256 applies SHA-256 twice. Okay.